Our next section in this chapter is about kinetic energy. Now, suppose you drop an apple. As it falls, gravity does a positive work on it, as indicated in this figure, and its speed increases with the fall. So, in contrast, if you toss an apple upward, then the gravity does a negative work on it, and because of that the apple slows down. So in general, whenever the total work done on an object is positive, its speed increases, and whenever the total work done is negative, its speed decreases. Now consider the apple of mass m falling through the air, and suppose that the two forces act on the apple. One is the gravity, which is mg in downward direction, and the average air resistance, F air. This is the air resistance, average air resistance. Now the total force is downward and the motion is downward because the apple is falling through the air, and therefore the work done on the apple should be positive. So after some algebraic manipulations of the equation of motion, we can find the total work done on the apple. W total is force times d, which is equal to the half mass V final square minus half mass V initial square. Now this shows that the total work is directly related to the change in speed according to this equation, and the quantity half mass times velocity square in this equation for total work done has a specific significance in physics. So we call this term as the kinetic energy K. So in general, the kinetic energy of an object is the energy due to its motion. So we measure kinetic energy in joules, the same units as work, and both the kinetic energy and work are scalars. So unlike work, kinetic energy is never negative, since mass is always positive and the velocity has a square value which gives always a positive value. Therefore kinetic energy is always greater than, or it can be equal to 0, and it is independent of the direction of motion or the direction of any forces. Let's see some examples involving the kinetic energy equation. Consider your kinetic energy when jogging. If we assume a mass of about 62 kg and a speed of 2.5 meters per second, what is your kinetic energy? So we are given your mass 62 kg and your speed, that means the v, which is 2.5 meters per second. And to find the kinetic energy, we can use the equation that we found. K is half mass times velocity square. So therefore kinetic energy is half, mass is 62 kg in here, and velocity is 2.5 meters per second square. Therefore it is 190, and this is an energy, therefore the unit of energy is joule. Now let's see one more example. A small airplane moving along the runway during takeoff has a mass of 690 kg and a kinetic energy of 25,000 joules. Now we asked to find the speed of the plane, and by what multiplicative factor does the kinetic energy of the plane change if its speed is tripled. Now in this question, we are given the mass of the plane and the kinetic energy of the plane, and we are asked to find the velocity. So according to the kinetic energy equation, kinetic energy K equals half mv square. So we are given the kinetic energy and the mass, and we asked to find the velocity. Therefore, we can find the velocity by isolating v from this equation. It is v square is equal to 2k over m. Therefore, v is equal to 2k over m square root. And we can substitute the value. 2 times k is 25,000 joules and m is 690 kilogram. Then we have to take the square root. Therefore, speed is 8.5 meters per second. So if you are given the kinetic energy and the mass, we can find the speed, and if you are given the mass and the speed, then we can find the kinetic energy. And in the next part, it asks what multiplicative factor does the kinetic energy k of the plane changes if its speed is tripled. That means v is tripled and we asked to find the k. Now according to this equation, k is equal to half mv square. Therefore we can say that k is proportional to speed square, v square. Therefore the kinetic energy depends on the speed square. Therefore if we triple the speed, then it should increase the kinetic energy by a factor of 9. So if we triple this is 3v square, which is 9v square, and therefore the kinetic energy is increased by a factor of 9. Now the relation between work and kinetic energy is given by the work energy theorem, which is the total work done on an object is equal to the change in its kinetic energy, which is delta k. So we learned kinetic energy is half mv square, that is kinetic energy. So delta k, change in kinetic energy, is half m v final square minus half m v initial square, that is the change in kinetic energy. So the work energy theorem says when a force acts on an object over a distance d doing work on it, then the result is a change in speed of the object and therefore a change in its energy of motion, which is kinetic energy change. Now let's solve some problems using this theorem. A 220 kilogram motorcycle is cruising at 14 meters per second. Now we are given the mass and the speed. Now what is the total work that must be done on the motorcycle to increase the speed to 19 meters per second? So we are given the mass of the motorcycle and the initial speed, which is 14 meters per second, and final speed 19 meters per second. And we are asked to find the total work done for the motorcycle to increase its speed to this final value. And now from the work energy theorem, we know that total work done is equal to the kinetic energy change. And from this equation, we know the mass, we know the final speed, and we know the initial speed. Therefore, we can find delta k, and it is going to equal to the total work done. So we can substitute the values now. W total. So we can take mass out from this equation because it is same before and after. Vf square minus V initial square. Therefore, W total is equal to half. Mass is 220 kilogram and V final is 19 meters per second square, and V initial is 14 meters per second square. So the answer would be 18,000, and the units should be in joules. Let's see another example of how the work energy theorem is used in practical situations. Now a 4.10 kilogram box of books is lifted vertically from rest a distance of 1.6 meters with a constant upward applied force, that is F applied, of 52.797 newtons, and we asked to find the work done by this applied force and the work done by gravity and the final speed of the box. Now the direction of motion of the box is upward because he is lifting the box. Therefore the applied force is in upward direction, and because of that work done by the applied force should be positive. And then the force of gravity, it is always in the direction of vertical downward. Therefore mg is vertically downward, and the work done by gravity should be negative because he is lifting the box, and therefore work done by gravity is in the opposite direction, therefore it is negative. And because of that we can find the total work done, which is equal to the work done by the applied force plus work done by the gravity. And from that we can find the final speed of the box using the work energy theorem, because the work done is equal to the kinetic energy difference. So we can find the final speed of the box using this equation. Now let's do the calculation. These are the given parameters: mass of the box, vertical distance delta y, and the applied force, which is 52.7 newtons. And in part A we have to find the work done by applied force and work done by gravity and the final speed. Now the equation for work done, which is W equal to F cos theta times D, distance. So therefore we can find in part A we have to find the work done by applied force, which is equal to the applied force times cosine angle. So now what is the cosine angle of the applied force? It is 0. Why? Because the applied force is in the direction of motion, so there is no angle, therefore theta is 0, and the distance is delta y. Now cos 0 is 1, therefore it is applied force times delta y, and we can substitute the values now. Applied force is 52.7 Newton, delta y is 1.60 meters, therefore applied force is equal to 84.3 joules. Now in part B we need to find the work done by gravity, which is Wmg. Again it is F cos theta times D. Now the force is mg, and what is the angle? It is cos. Mg is in downward and the motion is in upward. So mg is in downward but the displacement is in upward. Therefore the angle is 180 degree. Therefore it is 180 times D is delta y. Now cos 180 is minus 1. Therefore it is mg minus 1 delta y. Therefore it is mass is 4.10 kilogram, gravity is 9.81 meters per second square, minus 1, delta y is 1.60 meters. So we get a negative value which is 64.4 joules. Now we can find the total work done. There are only two forces in this box, that is applied force and the force due to gravity. So the total work done is work done due to applied force and work done due to gravity. So which is 84.3 joules minus 64.4 joules, which is equal to 19.9 joules. Now we know that according to work energy theorem, the total work done is equal to the kinetic energy difference, which is W total is equal to delta K, or it is equal to half m V final square minus half m V initial square. Now we know that V initial is 0 because it starts at rest. Therefore this term goes to 0. Therefore it is half m V final square. Now we are asked to find the V final. Therefore we can isolate V final from this equation. It is 2 times W total over m. Therefore V final is square root of 2 times W total over m. Now if we substitute the values here, W total is 19.9 and mass is 4.10 kilogram. We will get the answer for final velocity 3.12 meters per second. Now in this example, the initial speed was 0. He start at rest. But this is not always the case. Now let's see an example that considers a case with a non-zero initial speed. When a father takes his daughter out for a spin in a stroller, he exerts a force F with a magnitude of 44.0 Newton at an angle of 32 degrees below the horizontal, according to the sketch. And the stroller and the child together have a mass of m 22.7 kilogram. And we are asked to find the work the father does on the stroller when he pushes it through the horizontal distance d of 1.13 meter. And if the initial of the speed of the stroller is given, we are asked to find the final speed and to neglect the friction. Now our sketch shows the direction of motion and the direction of each forces. So the mg is directly downward and the normal force N1 is vertically upward, and the force exerted by the father has both vertical and horizontal components. So the vertical component of the force exerted by the father, so we can find the component of this force. The vertical component is F sine 32, but it is in the negative direction, y direction, therefore it is a negative value. And the horizontal component is F cos 32 and it is in the positive x direction, therefore it is positive. It is in the direction of motion. Now let's do the calculation. These are the known parameters. We are given this force and the distance d, mass and the initial speed and the theta angle, which is 32 degrees. And in part A we have to find the work done by the father and the final speed. Now let's find the work done by the father. Now from the sketch we see that the normal forces N1 and N2 and the weight mg, they are all in the vertical direction, which is, and the motion is in horizontal direction and the angle is 90. Therefore all these three forces do not do any work because they are at right angles to the horizontal displacement. Therefore the force exerted by the father has a horizontal component that does a positive work on the stroller. Therefore the total work is the work done by the father, which is F cos theta times d, and now the force is given 44.0 Newton and cos angle is 32.0 and the distance is given 1.13 meter. Therefore we can find the total work done, which is the work done by the father in this case, which is equal to 42.2 joules. Now we can find the final speed by applying the work energy theorem. So we know that total work done is equal to the change in kinetic energy. So we can use the total work done value here, and the mass is given and the initial speed is given, therefore we can find the final speed. So the only unknown in this equation is the final speed. So let's isolate the final speed from this equation. So half mv final square is equal to W total minus half mv square, therefore it is plus half mv square. Now V final square is, we have to multiply by 2 and divided by m. Now by substituting the values, W total is 42.2 joules and mass m is 22.7 kilogram, and initial velocity is given 1.37 meters per square. So by substituting those numerical values in this equation, we can find the final velocity as 2.37 meters per second. Now that's the end of the second section in chapter 7. So in this section we learn that the kinetic energy of an object, K, is half mass times velocity squared, and the total work done is equal to the change in kinetic energy. Total work done is equal to the change in its kinetic energy. Let's move to the next section of the chapter.